Hey guys, today we're gonna talk about work and energy extending from what we've learned in 1130, MN 1130, and we're trying to extend a bit and talk more about work and energy that involves fixed axis rotation. Okay. So first of all, reviewing what we've learned previously, what's the work of forces and couples. So the work done by a force F is given by integration of F times dr, where dr is the infinitesimal vector displacement of the point of application of F, and in the equivalent scalar formation of the integral it can be written as F cos alpha times ds. So meaning the angle alpha is the angle between F and the direction of displacement, and ds is the magnitude of vector displacement dr. Okay, that's pretty much what we've learned before. So now for a finite rotation, when the body is not moving, it's actually rotating, the work done by a couple M whose plane is parallel to plane of motion is m is equal to F times b. B is the displacement from the initial position to the final position, times del theta, which is the angle of rotation. Okay. Now let's look back at what we have learned previously of the work-energy relationship. The work-energy relationship, the work done in a system is equal to the change in internal energy, or W12 is equal to U12. So therefore we get the work energy equation W12 or U12 is equal to del T, which is kinetic energy, plus del Vg, which is gravitational potential energy, plus del Ve, which is elastic potential energy. Now trying to look a bit regarding each of these individual energies. So first let's start with kinetic energy. So we've learned before about the translational kinetic energy, which is basically half times m times v square, which is just the mass of the object, the rigid body, times the velocity of the body in that direction. Now when it comes to the fixed axis rotation, we have to think about the point about which the body rotates. So it's going to be half times the moment of inertia, I know the moment of inertia of the body, times the omega squared. So we have to think about the point about which the body rotates. So to find the moment of inertia of the body, we have to use this equation, which is the sum of times mi times ri squared. So which is basically the sum of all the rotational position of the body times its mass. Now when we combine both of them for a body that's translating at the same time it's rotating, we have to go back, we have to use both these formulas. So we combine them and we come up with this formula, which is just half times m times v bar square, where the v bar square is the mass center velocity. It is the point about which the body rotates, not the j. So we have to find the velocity of that point, and plus half times I bar omega square, where I bar is the moment of inertia of the body about its mass center. So we have to be careful it's not j, it's about which the body rotates. So when we extend it and combine them with the gravitational potentiality and elastic potentiality, which will basically remain the same because they are unaffected by the fixed axis rotation of general plane motion, we get this work energy equation, which is del T plus del Vg plus del Ve. So for this, which is the kinetic energy of the body, and this is the potential energy, and this is the elastic potential energy. So you have half m v bar final square minus bar initial square plus half I bar omega's final square minus omega initial square plus mg del h plus half times k times initial f my final which is the final extension minus the initial extension square. Now let's look at a problem. So we have a solid disk which is suspended from a rigid ceiling as shown. The massless string wraps around the cylinder and attaches at A. A linear spring runs from the center of the disk to the ceiling directly above. Spring stiffness is 50 Newton per meter. The radius of the disk is 1 meter. The mass of the disk is 2 kg. So if the disk is released from rest at the point where the spring is unstretched, find velocity of the center of disk after it has dropped 30 meters. Okay. So we are given these values. Now, if this string is cut here and it starts falling down, we have to find the velocity when it drops 30 meters. So we go back and we think about the energy equation that we learned about previously, which is del T plus del Vg plus del Va. So since there's no loss of energy, the internal energy of the change energy will be 0, and we'll have the formula which I've seen before, which is half m Vf square minus Vi square plus half I bar omega f square plus mg del h plus half k del f square minus del I square. So let's look at these values. Initially there's no velocity, so it is 0, and even initially there's no, sorry I missed a term here, which is going to be, so initially the angular velocity is also 0, and initially there's no extension, so we have to assume that the spring is initially unstretched. So we have the formula, which is half mvs square plus half I bar omega f square plus mg del h plus half k del f square. Now, since the disk rolled down the string, we know previously that angular velocity is v over r, right? And now, using the equation for mass moment of inertia, which is half mr square for a circular object like this, so the equation is half is equal to half mvf square plus half times half mr square v square divided by r square from here, which comes from here, plus mg del h plus half k del f square. Okay, so the mass of the object is 2 kilos. We have to find the velocity plus half times it's 2 kilos. Then the radius is 0.1 square, and here again we have to find the velocity. 2 times 9.81 times del h is given as 0.3, and since it's initially unstretched, we can assume that the extension is also 0.3 squared. So summing up all these values, we come up with this. Now when we combine this and find the value for VF, 3.64 2.375, we get 3.12 meters per second. So this is the value or the velocity of the center of disk when it drops 30 meters. Thank you.